All right, some pre-algebra section 5.1 here, dealing with rational and irrational numbers, and we're going to be estimating irrational numbers today. So again, just as a review, the difference between a rational number and an irrational number, okay, is that let's take a look based on number one here. Some examples of irrational numbers are the square root of 2, okay, or pi that we just kind of talked about. And if you put those in a calculator, square root of 2, you're going to see on the right there, it's about 1.414213, right? That number is just going to go on and on and on forever. So part A, based on what we know about pi, right? Pi, the 3.14 we were just talking about, is that the entire value? And the answer is no. Okay, the decimal is going to continue on forever. There's no end to it. Same thing with the square root of 2. Okay, there's just no end. These are irrational numbers. So your calculator can obviously only show so many digits, right? It just doesn't have enough space. It's impossible. It never ends. Okay, so part C, we just talked about what's the difference between the decimal forms of rational numbers and the decimal forms of irrational numbers. Okay, and I just want to make sure we're clear on this. So rational, the decimal must end or repeat. While irrational is just the opposite. Does not end or repeat. Okay, so part D here, the set of rational numbers and the set of irrational numbers together form the set of real numbers. Okay, so if we combine all rational numbers and all irrational numbers, we're going to get the set of all real numbers. Okay, there is such thing also, a totally separate group called imaginary numbers or complex numbers that you'll get into a little bit later, probably Algebra 1, but definitely in Algebra 2. Okay, so are there any numbers that are both rational and irrational? Is it possible to be both of these where the decimal ends or repeats and also it does not end or repeat? Right? No, that cannot happen. So these are two totally separate groups. If we were going to do a Venn diagram, we could have rational numbers in one group, irrational in another. Okay, there's no overlap there, right? Have you guys seen Venn diagrams where sometimes things may overlap? In this case, they don't. They're totally separate groups. There's no number that falls into both categories. Okay, and then down at the bottom here, even though irrational numbers cannot be expressed as a quotient of two numbers, right, like a fraction, it is still possible to determine reasonable estimates. Okay, so let's talk about how do we get an idea of the size of some of these irrational numbers. Irrational number, it must be able to be written as a fraction. Okay, so this includes all your whole numbers because you can always just put a 1 underneath the whole number. It includes all regular fractions, of course. It also includes, remember, decimals that end or have a repeating pattern. Okay, for example, like 0.3 repeating, right? That repeats forever. And we showed in the previous section that can actually be written as a fraction that would equal 1/3, and that, of course, being a fraction means that it's rational. Okay, again, think of rational. The beginning of that word is ratio, and a ratio is basically just like a fraction, a comparison of numbers. Okay, so it's easier to think of it that way, and then irrational numbers are just things that cannot be written as a fraction. So, for example, decimals that do not end or repeat. Okay, for example, like the number pi, right? Its approximate value, 3.1415926, dot, 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 it goes on forever. That's never going to end. There's no repeating pattern. Therefore, you cannot write it as a fraction, right? If we do what we did earlier in the sections, when we think about 10th place, 100th place, 1000th place, so on, that just never ends. So we cannot write it as a fraction. So that makes it irrational. And today we're going to talk about some another commonly seen types of irrational numbers as well. Okay, so let's take a look here. Number 2, can we use the number line? And we're going to go through some steps here. Can we approximate the value of the square root of 18? Right, the square root of 18. Okay, and let's say we don't have a calculator. We can't just type it in and get some decimal approximate. And we want to just kind of get a ballpark value for it. Okay, so here's a little process we can go through. Part A, which perfect square is less than 18, but closest to 18? Okay, so perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Okay, so 16 we know is 4 squared. Okay, which perfect square is greater than 18 but closest to 18? Okay, well 4 squared is 16, 5 squared is 25. Okay, so let's think about what is the square root of 16? Square root of 16 is 4. Okay, the square root of 25 is 5. So our value, right, the square root of 18 needs to fall somewhere between 4 and 5. And we can see it's a little bit closer to 4, right? Because again, 18 is closer to 16 than it is up to 25. So the square root of 18 should be in between the square root of 16 and the square root of 25. So I would say it's around 4.2-ish, 4.3 maybe. That would be a decent estimate, but definitely closer to 4 than it is to 5. Okay, and I did that just by knowing that 16 and 25 were perfect squares, and that my value of 18 was the kind of a value in between, but again, closer to the 16. Okay. Let's do a couple other examples. Okay, what about the square root of 42? All right, so the square root of 42, so the number we want, 42 is there. Okay, it's not a perfect square, so think of numbers that are perfect squares. Okay, 36 is a perfect square, right? The square root of 36 is 6. Okay, the next perfect square is 49. The square root of 49 is 7. Okay, so what would that mean about the square root of 42? Well, it's a little bit closer to the 6 than to the 7, so it might be around 6.4 or maybe 6.5. Okay, because again, it's right in between, pretty much right in the middle of two numbers that are perfect squares. Okay, I was looking for the 42, right? The 42, it's only 6 units away from 36, but it's 7 units away from 49. So it's probably a little closer to 6.4, but also fairly close to 6.5. All right, what about the square root of 98? Square root of 98. What's a number close to 98 that's a perfect square? Okay, 100, right? The square root of 100 is 10. And the square root of 81 is 9. Okay, so our value of 98, square root of 98 is going to be in between 9 and 10 and quite a bit closer to 10. So it might be like 9.9, 9.8, something like that. Okay, so those are just approximates, okay, again, without a calculator. Okay, you should be able to get a reasonably close answer. Okay, the next couple problems, they're saying go ahead and use a calculator. Let's round our answer to the nearest tenth. So with these, you just need to find on your calculator where the square root key is. And in some calculators, you would have to type the 18 first and then press the square root key. But on the newer graphing calculators, and I'm not sure about phone calculators, but you could type the square root first, then 18, and press enter. Okay, so let's get a value here. The square root of 18 on a calculator is 4.2. And it goes on forever, okay, 4.246, but if we round it to the nearest tenth, it would be 4.2. Okay, the square root of 42 from a calculator is about, that's what the squiggly brackets, the squiggly lines are, is an approximation, 648,074, so we would round that to 6.5 if we went to the nearest tenth. And then the square root of 98 on a calculator is about 9.89949. So rounding that to the nearest tenth would be 9.9. Okay, so it looks like our estimates were pretty good, right? I mean, we said for the previous ones, we said 9.9 for the square root of 98, and we went with 6.4, 6.5. It was actually closer to 6.5 for the square root of 42. Okay, can we use the method that we just did to estimate the value of a cube root? Okay, so cube roots, a little bit tougher to do in your head, but let's list a few, and I'm going to do a side note here. Some of the perfect cubes, so like 1 to the third power, so 1 times 1 times 1 is 1. 2 to the third power, right? 2 times 2 is 4, times 2 again is 8. 3 to the third power, 3 times 3 times 3. Right, so 3 times 3 is 9, times 3 again is 27. 4 to the third power, 4 times 4 is 16, times 4 again is 64. Okay, so these numbers over here, those are going to be our perfect cubes. Okay, so we need to be using cubes here instead of squares to estimate a cube root, okay, because we want to find the cube root of 20. So let's think similarly. Which two numbers is 20 in between? Okay, which two perfect cubes? So I know that 8 is really 2 to the third power. And I know that 27 we showed is 3 to the third power. So where would our value of 20 be? Okay, what to the third power is about 20. So we can see it's going to be in between 2 and 3. And it appears to be closer to the 3, right? So it might be around 2.7-ish, something like that. Approximately 2.7. Okay, just again, because it's definitely closer to the 3 cubed than it is to the 2 cubed. So that's kind of a way to estimate it just the same way. And I would suggest kind of getting these first 4 or 5 perfect cubes down. Once you get higher than that, you're kind of going to have to be using a calculator, but it's helpful to know at least how to come up with the first few. Okay, so let's think about this. Why is the cube root of 64 a rational number? Okay, first off, what is the cube root of 64? Okay, well, we see down here that 4 to the third power equals 64. So the cube root of 64 is 4. Okay, that's a rational number. That's a whole number, right? It could be written as a fraction. It's 4 over 1. Okay, it's 4. That's rational. Okay, but the cube root of 12, right? Cube root of 12. Okay, if we use the previous number line here, the 12 is going to be around here somewhere. So the cube root of 12 is again between 2 and 3, closer to 2, but it's in between, right? It's not a perfect cube. It might be approximately 2.3-ish, something like that. Approximate, right? But that decimal would actually go on forever if we got the real value. If we used a calculator, let me just do it just for fun here. I'm going to do the cube root of 12 and just see what we get. It's 2.2894, so it goes on forever. It's a never-ending decimal. Okay, that doesn't repeat. That makes it irrational. Okay, so that's the difference. Some cube roots are rational numbers, many are not. Okay, same thing with square roots. You have all your perfect squares that are rational numbers, but all the ones in between, all the ones that are decimals, are going to be irrational. Okay, and I just want to show real quick on these how to get the cube root. So I'm going into second. I'm sorry, not second. I'm just going into math. And then that's where you'll see the cube power and the cube root. So I was doing the cube root of 12. Pressing enter, and that was how I was able to get the cube root of a value using the calculator. Alright, so let's just do a couple extra checking our understanding examples here. So can we name the irrational number in each set? So we have 17 over 2, we have a square root of 8, we have a cube root of 8. Okay, so again, to be irrational, right? Think of an irrational. Irrational means like crazy, right? A crazy number is never going to end, no pattern, just goes on forever. So 17 over 2, that's a fraction, right? Definitely that's rational. The square root of 8, square root of 8 is not a perfect square, right? So it's going to be a decimal that goes on. But let's just eliminate the other option too. The cube root of 8, the cube root of 8, remember, is 2, because 2 times 2 times 2 is 8. So the cube root of 8 actually just equals 2. It's the square root of 8. Okay, again, since 8 is not a perfect square, when you take the square root, it's going to be irrational. Okay, number 8. We have some crazy long decimal, but it has a repeating 9 at the end. We have 6 to the third power, and we have the square root of 65. All right, so let's talk about these. So the negative 0.5789999, since it's repeating, right, a repeating decimal is rational because it could be written as a fraction. 6 to the third is just some number. 6 times 6 times 6, that's some normal whole number. Okay, but the square root of 65 is not a perfect square. It's not a whole number, because 65 is not a perfect square. The square root of 64 would be 8. But the square root of 65 is going to be 8 point something, and it's going to be going on forever, irrational. Okay, let's estimate some square roots without using a calculator. So the square root of 10, so I know the square root of 9 is 3. So the square root of 10 is just going to be slightly bigger, maybe 3.1-ish. Okay, I should probably use the squiggly approximates. What about the square root of 28? So the square root of 25 I know is 5. The square root of 36 I know is 6. Okay, so is 28 a little closer to 25, or is 28 closer to 36? So it's definitely closer to 5. So I'm going to say the square root of 28 is about 5.2 or 5.3, right? And again, that's because the 28 is closer to 25. Okay, and you can always draw the number line as well, like we did earlier. Square root of 73, let's think about that. So the square root of 64 I know is 8. And I know the square root of 81 is 9. So our numbers in between those, let's see, from 64 to 73 is 9 units. And then 73 to 81 is only 8 units. So I'm saying we're a little closer to the 8, maybe 8.4, 8.5-ish. Okay, so I could take either one. When you're estimating, it's not going to be perfectly accurate, but either one of those would be right. Okay, and then they want us to place each of these on a number line. So the square root of 10 we said was just barely bigger than 3. The square root of 28 was a little bit bigger than 5. And then the square root of 73 was in between 8 and 9, right? Yeah. Okay, so we can do some of this stuff, again, without a calculator. Some of it, obviously will be more accurate with a calculator. But we should be able to do some estimation and that kind of thing. Okay, so the assignment will be here is a 5-1 practice, numbers 10 through 15.